Hello. By now you should have learned that there are two ways to change the temperature of a gas. One is by heating, the other one is by doing work on it. In terms of energy, we can say that the increase in the internal energy of a system comes from the heat supplied plus the work done on the system. So see, the internal energy of a gas can increase either by supplying heat to it or by compressing it. This equation here is called the first law of thermodynamics. And you say, what? The first law of thermodynamics, the foundation on which the Industrial Revolution was based on? The equation that brought us the refrigerator and the aircon? Is just like that? 3 terms, no multiplication, no power, no square root, no nothing? Yeah, sorry to disappoint you. Yeah, it's that simple. Having said that, I know there are many students who have problem with this equation, and the reason is because they confuse these 3 terms. So let me try to make it very clear to you who these 3 terms are. Now, if your gas cools down, it means delta U is negative, because for the gas to cool down, the average KE must decrease, which means the total microscopic KE must decrease, which means the internal energy must decrease. So delta U is negative. On the other hand, if your gas becomes hotter, it means delta U is positive because you have gained internal energy. Now, if you supply heat to your gas, then Q is positive. On the other hand, if you withdraw heat from your gas, then Q is negative. Now, what about this term work done on the gas? Easy. If you compress the gas, work done on the gas is positive. If it's the gas that expanded against the external pressure, then work done on the gas is negative. So if the external environment wins, then work done on the gas is positive. If the gas wins, then work done on the gas is negative. Sounds very simple, right? So let me test you, yeah? So if heat is supplied to a gas, does the gas become hotter? Have you decided on your answer? I'm going to review the answer now. So if heat is supplied to a gas, what we are told is Q is positive. Whether the gas becomes hotter or colder depends on delta U. So having Q being positive doesn't guarantee that delta U is going to be positive. For example, you can supply 10 joules of heat, but if the work done on the gas is negative 30 joules, then delta U will still be negative 20 joules. So the gas can become colder despite heat being supplied to the gas. Get it? Now try this one. A gas has become hotter. Does it mean that it has gained heat? Have you decided on your answer? I'm going to review the answer now. So when we are told that a gas becomes hotter, all it says is delta U is positive. The internal energy has increased because the average KE has increased. Whether it has gained or lost heat is about Q. So can you see that delta U being positive doesn't imply that Q must be positive? Because there's still this term here. So we could be looking at positive 10 joules here, negative 20 joules here, and a positive 30 joules here. It's possible for a gas to become hotter despite losing heat thanks to a compression. Get it? Okay, now try one last one here. A gas is kept at constant temperature. Does it mean that there's no heat flow? Decided on your answer? I'm going to review the answer now. A gas is kept at constant temperature means that delta U is 0. But delta U is 0 doesn't mean Q is 0. It doesn't mean work done on the gas is 0. It just means that together, Q plus work done on the gas is 0. As long as Q and W are opposite in signs, then delta U will be 0. So for example, if Q is positive 10 joules and work done on the gas is negative 10 joules, then delta U will still be 0. So if you had problems with these 3 questions, it's because you're still stuck with the old habit that if you supply heat, temperature must go up. If you lose heat, the temperature must go down. You're now an A-level student. You have to remember that besides Q, there's also work. The earlier you got work into your subconscious, the earlier you'll master the first law of thermodynamics. Alright, that's all. Ta-ta!